Greetings. Welcome to my video lecture 4 on Laplace Transform. Today we'll be working on finding Laplace Transform using techniques, not necessarily using the definition. So let's see how that's going to play out. Let's look at, I've given you a couple of examples here. So let's look at having to take the Laplace Transform of t plus 1 to the third power. Now, here you need to recall two things. A is that a plus b to the power of 3 from the binomial expansion days, if you recall, and we're using Pascal triangle, was a cubed plus 3a squared b plus 3ab squared plus b cubed, if you recall. So you obviously need to know that to expand that. So you could write that as the Laplace transform of t cubed plus 3t squared plus 3t plus 1. Now, we all know that Laplace transform is a linear operator, so I could separate these and pull the constants out. So that becomes Laplace transform of t cubed plus 3 Laplace transform of t squared plus 3 Laplace transform of t plus Laplace transform of 1. Now, here you need to recall the Laplace transform of t to the power of n. See, that's why you need to recall two things. One of them is the binomial. The other one is what was the Laplace transform of t to the n that we learned, and I asked you to memorize. So Laplace transform of t to the n, if you recall, was n factorial over s to the power of n plus 1. So you don't have to use the definition for every one of these and take like an hour and a half to answer a question that could be done in like 15 seconds. So since you know that and that's what I mean when I say doing Laplace transform using techniques and not necessarily using definitions. And obviously remembering the Laplace transform of a whole bunch of fundamental functions. So here I can then simply find the Laplace transform of t cubed using, you could say, this formula. That will just be 3 factorial divided by s to the power of 3 plus 1, which is s to the power of 4, plus 3 times the Laplace transform of t squared will be 2 factorial divided by s to the power of 2 plus 1, which is 3, plus 3 times the Laplace transform of t is t to the power of 1, so it will be 1 factorial, which is just 1, divided by s to the power of 1 plus 1, which is s squared. And the Laplace transform of 1 is just 1 over s. So you see, you just found the Laplace transform of this expression without having to use definitions. All right, moving on to our next example. Same thing here. If I'm asking you to do e to the t minus e to the minus t squared, again, you will use a minus b quantity squared, which is a squared minus 2ab plus b squared. So Laplace transform of this expression would be, you just do it out, so be e to the power of 2t minus 2 e to the t e to the minus t, which is e to the 0, so 1, so it's just 2. Plus e to the minus t squared, which is e to the minus 2t. Again, if you use the linearity of a Laplace transform, you could write this as Laplace transform of e to the 2t minus 2 Laplace transform of 1 plus Laplace transform of e to the minus 2t. And again, you notice here, you could just simply write the answer because you already remember and know what the Laplace transform of these fundamental functions are. So your Laplace transform is 1 over s minus 2 for this, minus 2 times Laplace transform of 1 is 1 over s, plus Laplace transform of e to the minus 2t is 1 over s plus 2. So again, you notice that you could simply find the Laplace transform without using the definition. Let's continue our examples, couple of more. Evaluate the Laplace transform cosine of 2t. Now, here, I know how to write cosine of t using the inverse Euler identity, but if you recall, for cosine squared of t, I don't even need inverse Euler identity. I just remember from my trigonometric identities that cosine squared of t, remember when it comes to Laplace transform, the more linear your functions are that you're finding a Laplace transform for, it's easier because when you have powers, it makes the integration more difficult. So that's because some people may wonder, how do you think about that? Well, when I see Laplace transform of cosine squared of t, immediately I ask myself to avoid having to use a painful definition and a nasty integration by parts here. and sometimes that's even impossible to do, is that I think about, okay, how can is there an identity somewhere that I could use to take cosine squared of t and convert it to a linear definition of a cosine? And I remember there is such a thing, because I could write cosine squared of t as 1 plus cosine of 2t, it's called double angle identities, divide by 2. So if that's the case, then again you notice that Laplace transform of cosine of squared t could be written as Laplace transform of 1/2 plus 1/2 cosine of 2t. And that, you can then use linearity of a Laplace transform and say 1/2 Laplace transform of 1 plus 1/2 Laplace transform of cosine of 2t. Now, 1/2 Laplace transform of 1, Laplace transform of 1 is 1 over s, so it's 1 over 2s, plus, I keep the 1/2 out, Laplace transform of cosine of 2t, we remember, is s over s squared plus a squared. A here is 2, so it'll be plus 4. And again, we found the Laplace transform without using the definition. Now, looking at this one, Laplace transform of t squared e to the at, unfortunately here, I could try to figure out if there's any way I could do this without a definition, but thinking about this and thinking about some kind of an algebraic trick to break this apart, that attempt fails. You basically here have no choice than to actually use a definition and say that'll just be t squared e to the at, which is the function, times the kernel e to the minus st dt, and then convert the exponentials and go through some horrific integration by parts that I've done here, and ultimately get to the answer that it's 2 over s plus 2 cubed. Now this looks like an answer that it looks like it came from something. It looks like there's some kind of a pattern to this response. It's not a very erratic answer. And that's what brings us to our next discussion, is that it was found out, and mathematicians noticed that, and so did Laplace, that something very interesting happens when you try to find a Laplace transform of some function. Whatever that function is, here is t squared, it could be t cubed, it could be cosine of at, it could be anything, it could be another exponential. But it turns out that if you're trying to find a Laplace transform of some function, in time domain, of course, and that's being multiplied to some exponential, it's being multiplied to some exponential, it turns out that when you're finding a Laplace transform of a function multiplied by an exponential, it turns out, and they've noticed, that something very interesting happens to this function in its frequency domain, in its Laplace language. And what they discovered was when you multiply a function by an exponential in time domain, then in frequency domain, you end up with something very interesting. You end up with the Laplace transform of the function itself. Like, you could completely ignore the existence of e to the at. You just find the Laplace transform of that function and then evaluate that function at the end in terms of s and replace it with s minus a, whatever the variable is at the end. That's called the exponential shift property. So it was discovered that if you find a Laplace transform of a function multiplied by an exponential, which using the definition becomes very difficult to do a Laplace transform like that, but thank God, because of just nature intended it that way, that when you transform a product of a function and an exponential, in S domain, in the Laplace domain, you get a shift. You get a shift of a units in the opposite direction. So if it's e to the positive at, you get s minus a. If it's e to the negative at, you get s plus a. And we call that the exponential shift. Now, you could prove that, and I've proved it for you here by doing it, so you can look at it, but it just makes life a whole lot easier. For example, and I'll start with the example that we had at hand. You see right there, if I ask you to find a Laplace transform of t squared e to the negative 2t, let's say, you're going to say, oh, this is that exponential shift thing, where all I have to do is not worry about e to the negative 2t. all I have to do is worry about how would I find the Laplace transform of t squared. Now what's the Laplace transform of t squared? It's 2 factorial divided by s to the power of 2 plus 1, which is 3. Well, that's the Laplace transform of t squared, but there's an exponential here, which would mean that here I have to take s to s plus 2. Remember the opposite of the coefficient. So therefore, see how easy it becomes now? Instead of having to do this kind of integration by parts and have a tear in my eyes coming down from both eyes, little sad face there, I could very simply just use the exponential shift law and just take the Laplace transform of t squared and then evaluate it at s plus 2. So it becomes 2 over s plus 2 cubed. So it becomes very simple to do the integral. And you could see the same concept here, e to the 5t. Well, I know it's 1 over s minus 5, but you could look at it if you write it as 1 times e to the 5t. Laplace transform of 1 is 1 over s, and then you evaluate that at s minus 5. So by knowing this, you don't even need to remember the Laplace transform of an exponential. Or something that even is much more pleasant, because really finding the Laplace transform of this would have been really tedious. Laplace transform of e to the, let's say, negative t sine of t. Well, again here, instead of worrying about the definition here, all you have to say is, oh, they want me to find the Laplace transform of a product of an exponential with a function in time domain, which basically means all I have to do is find the Laplace transform of sine of t, and then evaluate it at as s goes to s plus 1. All right, so because of that negative coefficient 1 there. So again, I'm just using the exponential shift law. So basically you say as s goes to s plus 1. So what's the Laplace transform of sine of t? I ask you need to memorize that. That's just a squared, which is 1 in this case, divided by s squared plus 1 squared. So the Laplace transform of sine of t is 1 over s squared plus 1. But since it's got an exponential product in time domain, you have to remember to apply the exponential shift law to this, which means you have to drive s to s plus 1, and ergo, that's the Laplace transform for e to the negative t sine of t. So it's a very nice law to use. It's a nice property to use, and it will make a lot of Laplace transforms become a whole lot easier to deal with. This brings us to, and I've given you, of course, a whole bunch of problems to do here on this page. I've shown you how to do it by integration by parts, but nobody wants to do this. And try this, and you'll see how easy it is to use the exponential shift to evaluate all this. For example, in the first one, all you have to do is find a Laplace transform of sine of t, and then evaluate it as s goes to s plus 1. In here, all you have to do is evaluate the Laplace transform of t squared, and then drive s to s plus 2. In here, all you have to do is find the Laplace transform of cosh of t, and then evaluate it as s goes to s plus 1. So, and I've given you some hints about like what was the Laplace transform of cosh of t to begin with. So you could try these, and if there are some questions, I'd be more than happy to look at it with the rest of you guys on discussions. And same thing here, and this is an interesting example, and showing Euler's formula and how you could reduce this. Now, this is a proof of it, and I want you guys to look at it so you could see how you could actually use the Euler's formula to go through and find a Laplace transform of that thing. But again, you notice if you use the exponential shift law, it becomes very simple to do it. All you have to do is find the Laplace transform of the cosine function, which is s over s squared plus a squared. And then all you have to do is look at the shift and evaluate that as s goes to s minus a. Ergo, this problem. Very good. This is an extra credit type problem, and it's something interesting, and try to not to look at this. Try to just see if you could verify this, either going from left to right or right to left, whichever one you think you could do. But seriously, don't look at this that I've put here. You can look at it later, but try to do this yourself. It's called the change of scale theorem, and it turns out that the Laplace transform of f of at is 1 over a f of s over a. That's just how it works out. It's almost, this is like a proof. So it'll be interesting to see if you could come up with how you could do this. Obviously, you have to use the definition for this. So again, we can continue discussing this under discussions if need be. Same thing here, just more examples for you guys to work on. I've given you the 3 things you need to do this example. Again, you will just obviously not use the definition, but you'll write this and open up the e to the t plus e to the 2t to the power of 2, the binomial expansion, e to the 2t plus 2 e to the 3t plus e to the 4t, and then you multiply out the t e to the 2t plus 2t e to the 3t plus t e to the 4t. And here you notice that all of these are exponential shifts. All you have to do is find the Laplace transform of the t's, the t, the 2t, and the t, and just evaluate it here as s goes to s minus 2. Here s goes to s minus 3, and here s goes to s minus 4. And then you could easily derive that answer. And again, I would welcome discussions on any of these problems under discussions on Canvas. Moreover here, and I've given you what you need to start with, and I've given you the final answer. So you could practice all of these, and same thing over and over again. And I will stop here, and on my next video, I will introduce you to inverse Laplace transforms. Thank you.